Good afternoon, everybody. I hope that you guys are having a good start to your day. Um, I hope that this asynchronous format is something that you are able to work with. And, if you've got any questions and you need anything clarified, I always want you to know that you can contact me and I will schedule a time to meet with you. So, with that in mind, today's lecture is really kind of a continuation of last Wednesday's lecture. So today what we're going to be doing is, and this might look a little bit similar to you or a little bit familiar, what we are going to be doing today is we are again going to be learning how to draw a Lewis structure. Now, what makes today a little bit different is that today what we're going to be doing is we're going to be drawing a Lewis structure, Lewis structures, I'm sorry, with atoms with LP, LP, lone pairs of electrons. So what we're going to be doing is we're going to be figuring out where to put those electrons. Now, this first slide is one we've seen a handful of times. This is our main group elements and basically gives us a good idea of how many valence electrons we need to work with for each one of the different elements that we're drawing. Now, this is going to be a good foundation, a good thing to keep in mind. And I think this is a nice visual cue that you kind of have an idea of what it looks like already. And you have that with the help of being familiar with the periodic table and knowing group 7, 6, 5, and 1 and 2, respectively. So these different groups and those numbers, well, they correspond to the number of valence electrons. Now, drawing a Lewis structure of a molecule, well, we already know that process. Where it gets a little bit different is now what we're going to be doing is drawing a Lewis structure of an element or of elements, but we are going to be using elements with lone pairs of electrons. So our process is the same. What we need to do is we need to look at all of the atoms and all of the atoms that we have and all the electrons, the valence electrons that they have. We need to identify our central atom. And typically, this is going to be the one that's written farthest to the left, but immediately you're going to see that there's an exception to this. Then we're going to draw all other atoms surrounding that central atom. We're going to connect those atoms to our central atom through one line, which is representative of 2 electrons. We're going to place all other electrons until we reach our total. Then we're going to try to get each element to have a complete octet. Now, we talked about this as early as last Monday, the 24th, and then we talk about it again. Are there some elements that are exceptions to the octet rule? There absolutely are. Now, with that, whenever we need to, we might need to draw a double or a triple bond. So, this is our process. And I think that the more that you do this, the more comfortable that you get. We have about 5 different structures we're going to look at today and go through those. And the first one is none other than H2O, dihydrogen monoxide, if you want to use the appropriate molecular name, or maybe you want to call it what you call it every day, and that is water. Okay, so what I'm going to do is I'm going to toggle back and forth between this slide and our previous one because it will help us. Now, I'm going to do that throughout the entire presentation, so go ahead and uh, kind of get comfortable with that change and that going back and forth. All right, so if we go back to take a look at these elements, hydrogen and oxygen, what we will see is that oxygen has a grand total of 2, 4, 5, and 6 electrons. We got 2 hydrogen atoms, and each hydrogen atom brings 1 electron to the table. So what that means is that we've got 2 hydrogens, 1 oxygen. I'm going to go ahead and write the total number of electrons out here. That would be 2. And then I'm going to add an X here so that I make sure that I'm looking at oxygen, 6 electrons. So all told, that means we have 8 electrons to draw. Now, an important thing to remember right from the jump is that hydrogen is one of our elements that, well, breaks the octet rule. Now, how many electrons does hydrogen like to have? Well, it likes to have the one that it brought, and then it likes to share another one. So it likes to have 2 electrons. Now, as a little bit of a reminder, what does that mean when hydrogen is sharing an electron and it has 2 electrons around it? It has the same electron configuration as which element? A little bit of a spoiler, it's a noble gas. It has the same electron configuration as helium. Okay, so we've got 8 electrons here. Oxygen is our central atom. Now, like I said, typically your central atom is going to be the one that's written farthest to the left or first. This is one of those exceptions. And in part, that's just because hydrogen is kind of at the center of lots of exceptions. I'm going to clean that up a little bit. Let's go with, there's our oxygen. And now I'm going to draw hydrogen and hydrogen. Now, actually, you know what I'm going to do? I'm going to revise that. I'm going to draw one hydrogen on the left side, one hydrogen on the right side. Okay, so I like to keep a running total here. 8 electrons that I can possibly draw. How many do I have right here? Well, this has 4 electrons. So 8 total, I've drawn 4, so I'm going to subtract 4 from this. 4 electrons left to draw. Now, in the event that you're looking at this and you're thinking, where do the 4 electrons? Remember, this line right here is 2 electrons. And then this is also 2 electrons. So that's where my 4 electrons are coming from. Each single bond represents 2 electrons. So there's my structure of water with a total of 4 electrons drawn. I've got 4 left to draw. The fair question is, where do they go? And, to answer that, we can look at all the atoms that are there. We've got hydrogen. How many electrons does this hydrogen have? And you could look at it from the perspective of how many did it bring and how many is it sharing? Well, I like to go ahead and draw this big circle around hydrogen and then a big circle around this hydrogen. Well, that's got 2 electrons each. And then I also like to draw this to kind of show is anyone familiar with this sort of image, the Venn diagram? Those 2 hydrogens each have 2 electrons, and that oxygen has 4 electrons. So I'm going to erase all my circles, though, but I'm just really showing that hydrogen is in good shape. So these remaining 4 electrons, where do they need to go? Well, I'm going to put them on my oxygen. Now, with that in mind, oxygen, is in good shape. It's got a total of 8 electrons surrounding it. It's got 8 electrons surrounding it, so oxygen has a complete and satisfied octet. So this is a good preliminary structure. Now, one thing that I've mentioned previously, and I'm going to switch colors to illustrate this. I mentioned the space that electrons occupy. I'm going to erase that. I'm going to go ahead and draw dots to represent my electrons. So these are my 2 dots. I'm going to focus on the ones on the left here. These 2 electrons, what are they kind of gravitating towards? What are they pulled towards? Well, they're pulled towards the hydrogen. They're also pulled towards the oxygen. And so what that means is that these negatively charged electrons are pulled towards the positive nucleus of oxygen and hydrogen here. And so what that means is that a bond, if you want to kind of visualize what a bond looks like, it's really going to kind of look like this. Because in this shape that I'm coloring in here, this is basically like it's an illustration of where electrons can possibly be. Now, these other electrons, these and these, this and this, those two electrons, what are they gravitating towards? Well, the oxygen nucleus, and that's pretty much it. What that means is that these two electrons are going to fill a space that looks like that. And keep in mind, this is in three dimensions, the X, Y, and Z plane. And so I'm really sharing all of this because that's one of the reasons that whenever you see a water molecule, people draw it like this. Lone pair of electrons, lone pair of electrons. Because these lone pairs of electrons, they kind of fill a big area. And that, in a nutshell, is everything that's going on there. This is all of my 8 electrons drawn. My water molecule is good to go. And that's what I had to do. Okay, now I got my valence electron chart again. I went ahead and made copies of this in multiple places so that I could draw it in multiple places. I've got NH3 now. Okay, NH3, I'm going to go back and forth. I've got 1 nitrogen, 3 hydrogens. Little bit of a spoiler. I know that each hydrogen is bringing 1 electron, so that's going to be 3 electrons. Nitrogen. Well, nitrogen's right here. Nitrogen has 5 electrons, 5 valence electrons. So I'm going to write that out here. Now, one of the things that I always notice in this particular image, well, I do the same thing whenever I look at the oxygen, and I'm drawing water. This is a little bit of a trick almost, and it's like jumping ahead a little bit, but um, that's a pretty good model for kind of what we might be going through and going for. Now let's go ahead and draw the whole thing though, and put together our structure according to the rules that we've kind of established and agreed on. Nitrogen's bringing in 5 valence electrons. Each of our hydrogens is bringing in 1 valence electron. We've got 3 of them. We have a grand total of 8 valence electrons. Now, which is our central atom? None other than nitrogen. Okay. Now we've got to draw our bonds. And heck, I'll go ahead and, kind of distribute them evenly. Hydrogen, hydrogen, hydrogen. Okay. Now, are my oxygens, are my hydrogens, are they in good shape here? Yes, they are. Each one of my hydrogens here has a complete octet because it only needs 2. Even though an octet is 8, hydrogen is happy. It's got 2 electrons. That's all that it wants. That's all that it needs. Now, nitrogen, by comparison, nitrogen's got a total of 6 electrons. So, and I'm going to go ahead and do my accounting. 8 electrons that I had total to draw, subtract, this is 2, that's 2, that's 2. Well, I've got 6 electrons. 8 minus 6 is 2 electrons. I can erase this, erase this. I've got 2 electrons left to draw. Well, would I put any of those electrons, any of those 2 electrons on hydrogen? If I did, then each one of those hydrogens would exceed the octet. If I did something bonkers like that, well, then this one hydrogen has, well, 4 electrons around it. That's not going to go. But instead, if we put the electrons here and here, well, what does that mean for nitrogen? Nitrogen's got a grand total of 8 electrons surrounding it. And with it having 8 electrons surrounding it, does nitrogen have a complete octet? It does. So what we want to do is go ahead and call that a day. Now, it's worthwhile to think about this and say, all right, well, what does this actually look like? As kind of as much as possible. We've got our lone pairs of electrons. The same rules that we saw with this lone pair of electrons, the one where I have that kind of bubble going there, well, that's going to occupy a lot of space. And whenever I draw this big sphere, these electrons are going to push here and they're going to push here. They're going to be repelling one another. So these 2 electrons here are going to be repelling those and those down. So this is all, this big circle or this big balloon shape encompassing those electrons with these arrows pushing down. That's not a part of the Lewis structure. It just provides your Lewis structure with a little bit more definition. Now, with that said, this structure is good to go. I've got 8 electrons drawn. Nitrogen has a complete octet. Hydrogen has a complete octet. We're in tip-top shape there. Okay. Now, with that, valence electrons again. But now we've got sulfur, sulfur, fluorine. Okay. Now, if we jump back, where is sulfur? Oof. Sulfur is right under oxygen. Fluorine is our most electronegative element. And so fluorine is there. It's got 7 valence electrons. So, at first kind of blush at this, we got a lot of electrons to draw. Sulfur, each sulfur atom, and there's only one, has 6 electrons. Okay. Fluorine. Fluorine has 7 valence electrons. But keep in mind, this is 4 times that. So 4 fluorines equals 28 electrons. So 28 electrons plus 6 electrons is 34 total electrons to draw. Okay. Now, does anyone want to take a wild guess as to which is our central atom? Yeah, that's right. You got it. Sulfur. It's written to the left. There's only one of them. That makes it a little bit easier. So then nobody's coming up with a structure that looks like this. Instead, we're going to go with S, F, 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 and last but not least, yeah. Okay. This is where it gets a little bit beneficial to go ahead and keep track of your electrons. We had 34 total to draw. In my math, does that check out? 7 times 4, 14, 21, 28, plus 6, 34. I'm good. How many have I drawn so far? Well, 4 single bonds, each bond representing 2 electrons. We've got 8 electrons drawn. 34 minus 8 is 26 electrons. Okay, so I've got 26 electrons. Now what I need to do is ask myself, where am I going to put all these electrons? One thing that we can do from this point is we can say which of these atoms have a complete octet. Right now, sulfur has a complete octet. Now, I'll give you a little bit of a hint. There are some atoms, phosphorus and sulfur are great examples of atoms that can exceed the octet. What that means is they can have more than 8 electrons surrounding them. Now, with that in mind, when you're drawing a structure where there is an atom that exceeds the octet, I would strongly recommend that you don't start with the idea of, oh yeah, sulfur can exceed the octet. I would instead kind of put that in my checkbook and be like, I can revisit that later. But for the time being, what we want to do is try to satisfy every other atom's octet. And so we're going to go out to a fluorine. Doesn't matter which one. I'm going to start at this kind of 12 o'clock position. I'm going to put 2, 4, 6. So that's 6 electrons plus the 2 shared, so that fluorine has a complete octet. Then what I'm going to do is go over to my next one. 2, 4, 6. And then I still have that 8, that shared pair of electrons. Then, last but not least, 1, 2, 3, 4, 5, 6. Okay, so I got 8 electrons there. And then 1, 2, 3, 4, 5, 6, 8. Okay, so what I've done is I haven't accounted for the number of electrons that I've written out. I've just aimed to, have each one of them have a complete octet. Now I'm going to switch colors just so I can kind of keep track of what I'm writing. I'm going to put a check mark by each of my atoms that has a complete octet. Done, done, and done. Does sulfur have a complete octet? It does. Now I'm going to erase that check on sulfur though. And now what I'm going to do is subtract the electrons that I just drew. So I just drew those 6 electrons. Minus 6 is 20 electrons. Okay, now I'm going to draw, I just drew these 6 electrons. Minus 6 is 14 electrons. Then these 6 electrons minus 6, we're looking at 8 electrons. And then here's 2, 4, 6 electrons minus 6. And I'm down to 2 electrons. Okay, so a great question is, where do those 6 electrons go? And typically when you have an excess of electrons, you want to put them on your central atom. So using that as kind of a general, as a good rule of thumb is helpful. It's nice to have that. But another way to look at it is, and the way that I've always kind of thought about it is, you have 4 fluorines. Okay. Um, and I'm going to use a little bit of my own like personal experience. I've got several kids. And if I go to the gas station and I get gas and then I come home after, and I was like, "Ooh, I'm gonna buy one of my kids candy." Um, if I get candy for one of my kids, what are the other kids gonna do? They're not gonna be like, "Oh, I'll just ignore that." No, they're gonna be like, "Where's my candy?" And fluorine isn't exactly like a 6-year-old, but I always kind of think about it like, does it make sense to put 2 of these electrons on one fluorine as opposed to another, as opposed to another, as opposed to another? No, it doesn't. So that's one factor at play. Another factor is, like I said, there are some elements that are more capable of exceeding the octet. Sulfur and phosphorus are great examples of elements that can exceed the octet. So those 2 electrons, I'm going to put them on sulfur, because that sulfur can exceed the octet. So that one's in good shape. Now, with that, I'm going to say minus 2. Now I have 0 electrons. It's because I put them on my central atom, which was sulfur. Did I make any of the fluorines jealous in the process? Nope. Are they upset that one fluorine got electrons and the others didn't? No, they're fine. Okay, so here we go. Again, we got valence electrons. Now we got this atom. Okay. Now the key here that I've been kind of working on is we're drawing we're drawing molecules where one of the atoms in the molecule has a lone pair or lone pairs of electrons. You know, in our water, we had oxygen that had 2 lone pairs. Then we had ammonia, which is NH3, that had 1 lone pair. And then we had SF4, which had 1 lone pair of electrons. Now we've got ClF3. Okay, if we look at where chlorine is on the periodic table, right here. Fluorine, right here. Okay, so ClF3. So that means we've basically got 4 elements, and each one of them, or 4 atoms, let me rephrase that, 4 atoms, and each one of them has 7 valence electrons. So Cl, 7 electrons. F3, I'm going to say 3 times 7 electrons. Gets us to 21 electrons. So add these 2 together, and we get 28 electrons. Okay, so which is my central atom? This is, again, kind of a what makes the most sense. And, again, kind of going with my example of making my kids angry at one another. Well, really, they'd be angry at me. Chlorine, if we put that in the middle, well, then we can put fluorine here, here, and here. If we try to put fluorine in the middle, then how would we determine which one and why? Like, yeah. Now, with all of that said, one of the guidelines that I've asked you to go with is you're looking for the element that's written first um, in your formula. Another factor is your central atom is typically going to be your least electronegative element. Okay. So fluorine, that's our kind of extreme. That's our most electronegative element. Chlorine is going to be less electronegative than fluorine. They're both very electronegative, but chlorine's a little bit less electronegative, so that's why it ends up in the center. Okay, so we've got chlorine and fluorine. We've got 6 electrons. We've got 28 total, minus 6 that have been drawn. We have 22 left. What I'm going to do is I'm going to go ahead and look at my my most electronegative element, fluorine. And I'm going to go ahead and give that, or all of those, their proper number of valence electrons. So here are 6, plus 6 is 12, plus 6 is 18. So I'm going to go ahead and subtract 18 from 22, which leaves behind 4 electrons. Okay, now with that in mind, what does that mean? So we have 4 excess electrons. What did we do last time whenever we had excess electrons? Well, we had 2 extra. Let me clean this up a little bit. We had 2 extra electrons, and we put them on our central atom, sulfur. Here we're going to do the same thing. 1, 2, 3, 4. We've got 2 lone pairs of electrons on our central atom, which is chlorine. Now, before you say, oh, but you said phosphorus and sulfur. I did say phosphorus and sulfur. And let me go ahead and add a little bit of detail to that. The elements that are likely and capable or most capable of exceeding the octet, they start at phosphorus and basically go on from there. Anything after phosphorus on the periodic table has a good opportunity to break the octet rule. Now, I think a great question there is to say, well, then why do we have the octet rule? Because if you look at the periodic table, that leaves a ton of elements. Well, one of the reasons is that this is just an exception. The octet rule is the rule. There are exceptions to the rule. And when you think about most compounds are what are known as organic compounds, which means that they are carbon-based. So carbon-based compounds, organic compounds, typically are not going to exceed the octet rule. In fact, they are very, very rarely going to exceed the octet rule. But anything that's listed on the periodic table after phosphorus has a good chance to be able to exceed the octet rule. Chlorine being one of those elements that can. So here we've got chlorine with 2 lone pairs of electrons. It's good to go. Did we draw all 28 electrons? Yeah, we did. We drew our 6 for each one of our individual bonds, 18 for each one of the sets of electrons surrounding fluorine. Then we subtracted 4. We ended up with 0. Those last 4 being the 2 lone pairs of electrons on our chlorine. Okay, here is our last compound, SO2. Right. Let's jump back. SO2. So we've got sulfur, which is a little bit less electronegative, and it's listed first. So what we're going to do is we're going to write out SO. Now, sorry guys, but I kind of broke one of the rules there. I went ahead and drew my basic structure before I got my total number of electrons. Jump back. Sulfur rolls in with 6 valence electrons, as does each one of my oxygens. So that's 3 atoms, 6 electrons each, or 6 valence electrons each. 6, 2 times 6 is 12. 6 plus 12. We got 18 electrons to draw. Okay, I'm going to keep my counting over here. 18 electrons. I've drawn 4 so far. Minus 4. Okay, so now we're looking at 14. Okay, so I have 14 electrons. I'm going to complete my octet for oxygen. Okay, so that's 6. I'll subtract that. 8 electrons left to draw. Boom, 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 boom. Minus 6. And now we're looking at 2 electrons left to draw. Okay, well, if I do this, So what I've done here is I've gotten all of my six electrons. I've got two left. I put those as a lone pair of electrons on my sulfur. And so that means minus two, I'm at zero electrons. Okay, now looking at this, let's see. Fair question. Do my oxygens have a complete octet? They do. That's great. Does my sulfur have a complete octet? No, it doesn't. Okay, so that presents a little bit of a problem. Okay, now sulfur, if you remember, it can break the octet rule. But the way that it's going to break the octet rule is by having too many, more than eight, not less than eight. So when you have a molecule like that, let me show you this as a proposal. We've got, I already do this right here. I erased a pair of electrons. I put these two electrons as lone pair, or these two lone pairs of electrons on oxygen. I'm going to redraw that just so it looks a little bit better. Does sulfur now have a complete octet? It does. How many electrons have I drawn? Let's go ahead and add them up. I'm going to go with purple. There's two, so 4, 6, 8, 10. And I'm writing the total number of electrons at this point in time. 12, 14, 16, 18. Okay, so that's good. I've got the total number of electrons that I intended to draw, and that's great. Now, with that in mind, though, does this structure, like you could make the case, well, we've got a double bond on the left-hand side. Why don't we draw it on the right-hand side? That's a fair question. Now, in this case, we've got an issue where each one of these oxygens, they have kind of a different number of electrons. What I mean by that is, well, this oxygen right here, again, I'm going to kind of use that analogy or that comparison that I used with my kids. This electron right here, or sorry, this oxygen on the right-hand side, it only has to share two electrons. Whereas this oxygen on this side, that I've also used to use a star, I'm going to say, let's say, I'll label it A. Oxygen A versus oxygen B. Oxygen A has to share 4 electrons. Oxygen B has to share 2 electrons. Do you think oxygen A is going to get jealous of oxygen B? You're right, it will. And so, truth be told, well, what we want to do is kind of make them identical to one another if we can. So how can we do that? Well, one way we can do it is by dropping that, putting that double bond there. Okay, let's add up our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons. So we're in good shape there. Now, with those total numbers of electrons, um, is that good? Yeah, the oxygens are happy. Oxygen likes to have 2 lone pairs of electrons as opposed to 3. So each oxygen is happy. But what about sulfur? Sulfur is breaking the octet rule again. Oh, man. But is that a problem? No, it's not. Because sulfur can exceed the octet. And, you know, you could look at this structure and the previous one and say, oh, well, which is better? Um, Sulfur in every atom with a satisfied octet, or, every 2 of the atoms breaking the octet, and um, one of them breaking the octet and the other 2 being happy. And the answer is, in this case, this is the ideal structure. Now, you're probably looking at this and wondering, well, how do I know what to expect, for molecules going forward? Well, for what we're doing, this is one of those funky ones that I want you to be familiar with. Everything else that you'll see on quizzes and exams and activities, those will all be pretty clear in terms of what to expect from them. So this is one where it's like, well, that's a little bit odd as how that's done, but this is one of the few exceptions. Okay, so what we've gone through is SO2, ClF3, SF4, NH3, and H2O. All of these are molecular compounds. All of these molecular compounds have a lone pair of electrons. Some of them have multiple lone pairs of electrons, either on the central atom or then, if we talk about those with fluorine, they have multiple lone pairs on adjacent atoms. I think that it's good to now look at and think about what are these compounds actually called also. We've got water, but, well, that's dihydrogen monoxide. If we jump ahead, NH3, well, nitrogen and 3 hydrogens. That's nitrogen trihydride. This has a common name of ammonia, but either way, you can go. SF4, sulfur tetrafluoride. Does that name say anything about a lone pair of electrons? No, it doesn't. It says the number of atoms and the identity of those atoms. ClF3, chlorine trifluoride. Again, chlorine has 2 lone pairs of electrons. Pretty neat, but that's all that it is. Then SO2, sulfur dioxide. 1 sulfur, 2 oxygens. We use the prefixes. Why do we use the prefixes on all of these compounds? Because these are covalent or molecular compounds. Okay, I hope this is helpful, and I hope you have a good one. All right, everybody. See ya.